Welcome everyone for the day 2 4-note first session. The topic is electrochemical synthesis of green ammonia. In this lecture, the objective of this lecture to talk about the concept of green ammonia, the principle of electrochemical synthesis of ammonia, the advantages and challenges associated with electrochemical ammonia generation, then what is the recent advancement and research opportunities in electrochemical synthesis. So at the end of the lecture, you can able to understand what is the importance of green ammonia, then electrochemical synthesis process, what is the advantage pertains to the electrochemical green ammonia synthesis, what are the challenges and research focus. We are going to see some case studies and future outlook related to the topic I am covering today. As you all know that yesterday we had discussed about John and myself discussed about the ammonia generation through green route as well as the conventional route. So the Haber-Bosch method is the proven method. The method evolved 100 years back from the chemists Haber and Bosch to come up with the steam methane reforming with along with the ammonia generation from the Bosch kind of reactor. So in the steam methane reforming process, we are converting the methane, which is present in the natural gas, into, I can say, hydrogen and the CO2. The hydrogen is taken into the Haber-Bosch reactor, where the hydrogen reacts with the nitrogen. Nitrogen comes from the air. As you all know that about 79% by volume nitrogen and 21% by oxygen in terms of volume. In terms of mass basis, 77% and nitrogen and 23% by mass. So the nitrogen, to react the nitrogen and hydrogen to form ammonia, you need certain kind of operating conditions. That is, the pressure and temperature plays a major role along with the suitable catalyst. So in the Haber-Bosch reactor, the operating temperature is 350 to 450 degrees centigrade. The operating pressure varies from 200 to 350 bar. 300 times or 350 times the atmospheric pressure. You know that atmospheric pressure is equals to 1.013 bar, which is equals to 1.013 in 10 power 5 Pascal, which is also equals to 1.013 into Newton per meter square, 10 power 5 Newton per meter square. So by maintaining the conditions in the Haber-Bosch reactor at a temperature of 350 to 450 and a pressure of 250 to 350 bar, we can, by keeping some noble catalysts, the proven catalysts, so far, they are tried with several catalysts, thousands of catalysts, finally come up with a ferrous kind of catalyst, which is able to give the maximum generation of ammonia, about, I can say, 85 to 90%. That is the proven method. Yesterday, we have seen some of the green methodology, where I spoke about, I can say, and who also in the lecture, he has mentioned that green method of producing ammonia by keeping the Haber-Bosch, by only thing the modification, by avoiding the steam methane reforming, we are electrolyzing the water into hydrogen, then nitrogen comes through the maybe I can say through the membrane processing absorption method, where nitrogen and some oxygen is separated out. Nitrogen can be used in the Haber-Bosch reactor. In that method, we are eliminating the carbon dioxide. Eliminating the carbon dioxide completely. The type of ammonia we are getting by using electrolysis along with the Haber-Bosch reactor is free from carbon. So that's why it's called green ammonia. And another route also we have discussed yesterday. We are going to keep the electrolyzer. Then by keeping the electrolyzer, it can do both, I can say, electrolysis, producing hydrogen, and also in the same reactor, we are going to produce the ammonia by allowing the nitrogen as an inert for creating the plasma ionized gas. So something like the way in which we are producing the power in the engine, both the energy generation and power generation happening in the engine, same way. We have in our institute, we have created a facility where the generation of hydrogen and the reaction of hydrogen with nitrogen in the presence of the ionized medium, plasma medium, we are going to create the ammonia. Yesterday I have discussed that one. So electrochemical is a method people are trying to move that from the SMR method of producing hydrogen into electrochemical method of producing hydrogen to produce the ammonia. So it is advantageous in terms of, I can say, not producing any COX emissions, CO1, CO2. There are some problems associated with integrating the solar and wind with, I can say, the electrolysis. Then, if you see the Haber-Bosch process, you can able to produce the ammonia at a constant rate, whereas through green ammonia route by using solar and wind, which yesterday we have seen that the continuous supply of energy for dissociation is very much important for producing the hydrogen from water. So that is the challenges are available. And in terms of, I can say, electrochemical method, so this is the conventional method. This is the conventional method. So it is producing not only ammonia, also there are CO2 will come up. Along with that, because you are reacting at high temperature, the oxides of nitrogen also will come up. So this is oxides of nitrogen is highly dangerous pollutant in terms of you have seen that in today's newspaper also in Delhi. Still there, I can say the pollutants and the visibility is the issue for them. They are asking the school administration to conduct the classes through online because of the major pollutants of oxides of nitrogen. When it reacts with the solar rays, it produces photochemical smoke. So this is not only producing CO2 and also producing oxides of nitrogen because the nitrogen which is present in the air, which also reacts with the oxygen along in the reactor. So there is a possibility that the oxides of nitrogen also will come out. If you see the electrochemical system, it has three components. We have anode, cathode, and cathode in the electrolyte. So if you miss any one, you cannot able to do the desired reaction. So the purpose of anode and cathode, I can say, it is something like it can come across in our battery also. There is anode and cathode. But it is entirely different than the battery because in the battery you have stored the energy that can be delivered whenever is necessary. Whereas in this system, we are going to produce the electricity on board, you can be able to generate it. No need to store the energy. When you give some kind of the hydrogen or water, then it will be converted into. The purpose of the anode is nothing. Anode is a positive terminal. Cathode is the negative terminal. The purpose of the anode is to not only for, I can say, dissociating the water into hydrogen and oxygen, it will permit only, I can say, they will produce the positive ions. And the purpose of the electrolyte is, it will permit only positive ions to the cathode. So if the electrode is not there, then there is no reaction. There is a pathway is going to along with nitrogen and O also minus will be coming into that. The process is not going to be complete. So the purpose of anode is to ensure that it is producing positive and negative ions. The negative ions we call it the electron. So flow of current, we call it as a flow of electrons called current. So it will be not going through the electrolyte. Electrolyte will not permit the electron, it will permit only positive ions. The positive ion goes to the cathode where this negative terminal. Then the electrons goes into the circuit and enter into the, I can say, cathode for the reaction. Here, whatever with the hydrogen comes out through the electrolyte from the anode is going to combine with the nitrogen, which will be sent into the cathode side. So this is called anions. This is called cations. This will tends to anions will have, you can say, it is going to send the positive things. The anode cathode will tends to keep the negative ions. Whenever the electrons along with the positive comes into the cation side, then it will be reacted producing the. So this is the way all the fuel cell or electrolyte systems are currently working on it. In terms of fuel cell, what is the difference here is in terms of hydrogen fuel cell, you have the electrolyte, there also you have anode and cathode. Here the hydrogen will be sent into the system. Hydrogen ions will be through the electrolyte. It goes to the cathode. Electron will be coming to the cathode via the circuit. Here the H plus is there. So you are providing oxygen into the cathode. So hydrogen, I can say, reacts with the oxygen, producing the water along with the electricity. So the electricity, the power, the voltage or the current comes out from the circuit is going to be taken for the power generation. There's nothing but a power comes out from the electricity.
So here demand increases based on the demand supply also.
So the electrochemical reactors, you can see here, it involves the conversion of nitrogen, water into ammonia using electricity. So here, the input, you need a electrolyte, you need an anode, you need a cathode, you need a medium for anode, you need a medium for cathode. In order to aid the reaction, you need electricity. So if you are taking the electricity from the grid, well and good, we are going to get a continuous power, no issue at all. Till now it is working perfectly. But the electricity comes from the circuit to the conversion node. The CO2 is going to be through CO2 because we are generating CO2 in conversion plants. Okay. So we are finding out, we are not going to modify anything here. The way in which our electricity is applied to the electrolyzer, if it is from green, from solar or wind or any other renewable source, it's called green ammonia. Okay. So the reaction here is nitrogen reaction happens here. Normally, cathode, the process happening is a reduction reaction. The anode is an oxidation reaction. And here, the hydrogen reacts with the nitrogen. N2 reacts with, can say, hydrogen. Because this is the reaction happening at the cathode side. Okay. So this is the reaction happening at the anode side. This is the oxidation reaction. Oxidation reaction is the OER happening at the anode. What exactly you are doing? You are supplying high, I can say, current into the electrodes, particularly in the anode side. So the high electricity will be used for dissociating the water into oxygen, 1 mole of oxygen and 4 H plus ions and 4 electrons. The electrons will be comes out to the external circuit, entering into the cathode. Other reaction is called reduction reaction. Reduction reaction normally happening in the cathode side. So here the nitrogen which will be sent into the can say system either from the cylinder or from the PSA. But we need a desired pressure to ensure that the nitrogen reaches into the system. So normally what they are doing is they are separating out the nitrogen and oxygen from the air. Nitrogen is compressed to some pressure in the cylinder. Then whenever the nitrogen is needed for producing ammonia, you need to maintain some enthalpy between cylinder and the system. So no electricity is going to flow into the system. Okay. So we are producing. So what is nitrogen reduction reaction? So the core of this process is the reduction reaction where nitrogen from the air is reduced to ammonia at the cathode. Okay, this is the reaction happening. So already H plus 6 H plus through the electrolyte, it is entering into the cathode. Then 6 electrons from the anode. Go to the slide. Here, so the H plus comes from the anode, electrons comes through the external circuit, the nitrogen is available, you are supplying nitrogen from the cylinder. Okay, so from the air you are separating out the nitrogen that is going to be sent to the cathode side. The process is happening here. This is called reduction reaction. Okay. Similar to this, the hydrogen evaluation reaction is a side reaction. Not only I can say we are producing ammonia, sometimes the hydrogen is not going to find a suitable nitrogen, then there will be a possibility of I can say hydrogen also comes up. So the ammonia formation mainly due to how many moles of hydrogen along how many moles of I can say nitrogen available. If the nitrogen doesn't find a suitable number of nitrogen, it will convert it into nitrogen. So that way you can say that if the nitrogen is not supplied, you can able to produce the hydrogen. So what is the application? If you want ammonia, you supply nitrogen. If you want only hydrogen, no need to supply nitrogen into the cathode side. So developing, so in order to aid the reaction, in order to reduce the activation energy, right, to need for aiding the reaction, we need to select the right catalyst. Okay. We come to the electrocatalyst. As you all know that catalyst is a substance which is not going to burn or which is going to be take part in the reaction, but by keeping the catalyst, we are able to reduce the amount of energy needed to do the process. So if the catalyst is not there, you need to provide more energy from the surroundings. The catalyst or the proven catalyst, something like the Haber boards, we are using a ferrous kind of catalyst. The purpose of the catalyst is to ensure that minimum energy can be used for producing the ammonia. So the catalyst plays a major role for any kind of electrolysis as well as the ammonia generation. So electrocatalyst is a material that accelerates the electrochemical reactions on electrons. That means it will accelerate the process. Suppose the process going to happen without the catalyst going to happen for 5 minutes. You want to increase the reaction rate, you want to reduce the activation energy of the process, you can use some kind of the catalyst is going to support for the process. And also need to select a catalyst, maybe noble, and also you can find out some catalyst which is lower in cost. So because the amount of catalyst you are going to use for the process, not in terms of few grams or something, we go for a few tons of, I can say, ammonia generation in terms of tonnage of catalyst you are going to use it. So the amount, the cost you are going to invest for buying the catalyst also plays a major role. So you need to do some kind of study in catalyst selection. There are n number of ways you can select it, but for this process, what is the type of catalyst you need for to initiate the process as quick as possible. And also the catalyst should have the cost, should have the operating cost or the capital cost, should have to reduce it by selecting the right catalyst. So electrocatalysts are commonly made from metals, noble metals or platinum, palladium, nickel, non-metallic metals or carbon-based materials and metal organic frameworks. Normally, what currently we working on this in this electro type of catalyst, is there any possibility, as Reddy yesterday posted a question that, sir, I have a problem of recovering the material which is there in the solar beam. So there are a lot of precision metals are present over there, particularly platinum, palladium, nickel, so many elements are there. So you can able to recover it. Minimum energy can be spent on the system can be designed to recover the highly precious materials are present in the process or the waste product comes out from the electrical and electronic waste, which is not going to be utilized further. There you have a lot of, I can say, scope in utilizing the reuse the catalyst or reuse the material for as a catalyst for this one. Because here, when you want to employ this system, the renewable energy system, maybe after 10 years or 20 years, there are n number of solar panels will be available. So they are going to scrap it. So there the demand is there for the catalyst. So you can find out some method in which separate out the different non-metallic or metallic elements present in the electrical and electronic waste. Lot of, you can say, in the battery we have the lot of precious metals are there. Then mobile phones, then so many the waste that comes out. You see that here to the, I can say, dumping out, right? You cannot see that what are the different waste are coming out, but it has the energy in terms of to convert into a fuel, or it can recycle it to convert into a good product also is possible. Recent research focuses on material like transition metal, nitrates, noble metals, non-metallic catalysts that can effectively bind nitrogen and promote its reduction without significant changes. So what we have tried is we have used some kind of the activated carbon which comes out from the waste toner, right? The printer. So there are a number of, I can say, maybe you can reuse it for some time. After that, the toner is going to be thrown into the environment, right? So you can find out some noble metals are present in the toner. Also that the unused, the cartridge, I can say activated carbon, right? that has the possibility. I think Lakshman has did some work on that. I think he has used that as a converter into catalyst by adding some catalyst from metal impregnated the catalyst in that the waste material. He has enhanced the reaction in the gasification. So you can find out whether I am going to use the new material or I am going to spend a little amount to use the material which is available, which is abundantly available on the environment without much utilization. So the material selection, the selection of catalyst, you need to go different catalysis study, like you need to go find out what the operating temperature. For doing so, you need to find out the TGO, thermogravity analysis, what is the temperature, operating optimum temperature in which the catalyst is behaving well. Because ultimately, if you add 1 kg catalyst into the reactor, that's not burn it. So after several years of trial, I don't want the catalyst to be underutilized. So I want same amount after several years. Okay, so catalyst is a substance. It will only aid for the activating the reaction, but not taking part in terms of combustion or something. Okay, so need to do the thorough, I can say, literature survey or the proven catalyst. Suppose you are going for new materials, you need to do a lot of catalyzation. You need to do the TGS study. You need to do the, I can say, exotic study. You need to do the, I can say, some scanning under microscope to find out the particle size or maybe the porosity and maybe temper, so you can employ. There are several catalyzation methods are available to ensure that this catalyst is going to perform better before you take it to the process. So here we are back. So we are going to talk about different, I can say, after the catalyst, we are going to see the different, I can say, electrolytes. So there are 3 components plays a major role. One is the anode, cathode, and electrolyte. Then the electrolyte, the selection is also plays a major role for converting water into hydrogen or converting water into ammonia. There are several, I can say, electrolytes are available, solid electrolytes, maybe nitrate-based or sulfate-based electrolytes are available, and molten salt electrolytes are also available, membrane electrolytes are available, but each one has an operating temperature. Maybe if you cannot go beyond that, then if you go below that also maybe you cannot get the desired outcome. Okay, so ammonia synthesis rate, if you talk about the solid electrolyte, so how much per centimeter square of can say electrolyte you are going to use it. So 5.57, this is 201. You can see that the molten salt electrolytes better than among these 2, solid electrolyte and membrane electrolyte. Ammonia, additional detail is the ammonia synthesis with the proton supply from hydrogen, gas and anode. So here, in that method, we need to use the hydrogen for producing the ammonia, not water. Okay. Then molten salt electrolyte. At 4400 degree, we are able to get the conversion efficiency of 72%. Okay. Then for membrane electrolyte, 50:8 ratio of catalyst we can, because normally the membrane electrolyte we call it the polymer electrolyte membrane. Normally you come across PEM fuel cell or PEM electrolyte. There we are using the membrane called Nafion membrane. It will permit only positive ions, not negative ions. But in order to increase the reaction, we are coating some kind of the noble catalyst on the membrane to further enhance the reaction. Okay. So this is alkaline electrolysis fuel cell. The only changes here is, okay, say the type of electrolyte you are going to use. Here we have anode and cathode. So this type of electrolyte, maybe I can say alkaline electrolyte cells. Maybe I can say lower cost, higher efficiency, sensitive to CO2 contamination. Suppose we are using methane or any kind of methanol for producing something, hydrogen or something from this, then the CO2 contamination is the issue. But it is very low compared to other type of electrolyzers. This is going to be much better than that, but it has some advantage and drawback also. Then proton exchange membrane is a well proven and this membrane electrolyzer, proton containing polymer membrane electrolyte. So here we have the membrane. Normally, the membrane name is called Nafion. The cost of the membrane is very I can say the cost is very high. So by it's something like a sheet, a plastic sheet, or maybe the carbon paper, something like this. We are going to keep inside in between the anode and cathode. The purpose of the membrane is to permit only positive ions. Electron, the negative ions will be coming out to the cathode. Okay. So we call this GDL. Okay, GDL, we can say the gas diffusion layer. We call it the gas diffusion layer. The gas in the form of sending water, the hydrogen, the gas to pass through the gas diffusion layer to react to ensure that only positive ions are going to the cathode. Okay. So here the method used for producing hydrogen. Suppose you want ammonia, you can allow hydrogen from the surrounding. Then there is a operating condition needs to be modified so that you are able to get it. The problem, the question is, whether you are going to store the hydrogen in ammonia or you are going to use hydrogen as it is. So accordingly, you can give the use. Suppose we are putting nitrogen in here, you get ammonia. Nothing can be provided in the cathode. From the water, ultimately you will get only nitrogen.
What about this membrane cost?
It's expensive, very expensive. So
Life?
Life is depends on the temperature, and maybe I can say there is a possibility that the opposite reaction also going to happen. So membrane, how you are going to maintain the operating temperature and pressure space because it's something like sandwich. So this and this can be sandwiched, in between this. Even the pressure applied over this also plays a major. So normally, if you operate at a normal, I can say temperature of ambient temperature, it will not create any issue. But the membrane, the Nafion membrane is going to coat one side, one catalyst supports for anode, another side you are going to support the catalyst for the cathode. So the catalyst coating also plays a major role. Sometimes if you when you apply for a coating of certain micron nano thickness, then we need to ensure that the catalyst is coated on the thin film. Okay. So the life depends on the catalyst material also and operating temperature and pressure also. Because we are sending nitrogen from the surrounding at some pressure of 5 to 10 bar, then the Nafion also encountered with that, exposed to that pressure. So the solid electrochemical cells similar to our battery, we have the cathode, anode and cathode. There are different materials they are using in the anode and cathode also. Even people are suggesting to go for graphite. So graphite is a good material for conducting the ions. So even the waste materials available in the environment, you can convert it to a carbon electrode. We can use it for because it's spending money like in the silver, right? So it involves the cost also. But if any material which is available, abundantly available, it's not going to be utilized, you convert it into a material where you fabricate in the form of the required size as anode or cathode. Then you can able to reduce the cost of the plant. So advantages: high stability, compact design, high interfacial resistance, limited on ion conductivity. So there are we are going to compare the three, I can say, electrolyzers or electrochemical method. The first one is the alkaline, proton exchange membrane cell, and solid state cell. So here we are considering that the parameters electrolyte. Here the electrolyte is alkaline. That's called KOH, NaOH, right? And similar to that, you have any property which has alkalinity nature. That also you can bring it in the as an electrolyte. But alkaline is a proven electrolyte which is going to give the maximum efficiency. Whereas the proton exchange membrane cell, I said already, there's an Nafion membrane, and it is something like in terms of few micron size thickness is there. Through the sheet, the positive ions are exposed to the, I can say, send it to the cathode. So the operating temperature for the alkaline is 60 to 80 degree. Here it is 50 to 80. So with operating temperature plays a major because during the reaction, there is a possibility of water formation happens, right? There may be the fuel cell. Here also we are providing some amount of energy for this high temperature or high intensity current is passed into the electrodes. So the temperature you need to maintain that 50 to 80 degrees. Here, so the electrolyte is solid oxide, zirconium is electrolyte. The temperature of solid state is 500 to 800 degrees centigrade. The ammonia production rate is can say it's moderate. Here it is very high. Proton exchange. The solid state is also very high. The material cost is a nickel based. The electrodes are made up of nickel. Here platinum. So you can use, there are different materials are there. So if you want to do some kind of research in a materials perspective of cathode and anode, there are a lot of scopes are available. So if you have, you can say I found some new materials which is going to give the performance equivalent to the platinum or nickel or better than that. Will have a, you can say your work may be appreciable. Alkaline, the current consumption is 500 to 700 milliamps. Proton is about 5 amps. This one solid state is almost 5 amps. So to keep the same current consumption, solid state electrolytes are better than the alkaline electrolytes. But it is in terms of cost wise, low cost, mature technology, is a proven technology. Proton is high efficiency, compact in design. Here, solid state is high efficiency, scalable for large products. In terms of cost, this is going to be higher than PEM, then this is going to be lower. So, challenges, low current coming out from the system, or you need to, in terms of fuel cell, if you want to produce the electricity, and low current is coming out. If you want to use the same fuel cell as an electrolyzer, then you need to have the, I can say, challenges is low current needs to be utilized, but whether it is possible to dissolve it, that's the problem. Then the corrosion, because the alkaline, there is a possibility of corrosion of the electrodes or other components in the electrolytes. So high, the cost is very high, and there is a possibility of membrane degradation. So it's exposed to the different operating conditions. Okay. Here, higher operating temperature, naturally, when the system is exposed to high temperature, 500 to 800 degrees, so there will be a loading or deloading happens. So naturally, the material degradation happens. So what is the advantage here is, so here the current consumption plays a major role. So there the scope for using the renewable energy, solar, wind, or tidal, or geo, whatever is available. Suppose you want to establish a system at a place where near Thoothukudi or the Rameshwaram, where there are plenty of, I can say, a possibility to extract the wind energy or solar, or sometimes there's so much of tides are coming out, so you can able to convert that into electricity. Then you can able to reduce the energy consumption. Then the lower electrochemical ammonia production can potentially consume less energy compared to Haber-Bosch process. Naturally, they requires high temperature pressures because Haber-Bosch requires around 500 to 600 degrees centigrade. Pressure is about 200 to 300 bar. Here you are consuming the high energy. Here you are consuming the low grade energy. So this can lead to reduced operating costs and smaller carbon footprint. Ambient conditions. Electrochemical ammonia synthesis can be conducted under mild conditions, ambient pressure and temperature. So that is not possible in Haber-Bosch because we have to maintain the reactor at a high pressure, 200 to 300 bar. So here you can able to produce ammonia at our ambient pressure and ambient temperature. Even at 25 degree or 35 degree, you can able to produce it. This can reduce the capital cost and process efficiency. The electrochemical ammonia synthesis can be scaled down for decentralized production. That means, what is the advantage here is you need to, instead of producing the, I can say, ammonia at one point and distributing through pipelines or through transportation, there, if you go for distribution, the electrolyzer along with the system with for ammonia generation, then you can able to generate ammonia at locally, every district or every panchayat, you can able to generate it. Because the transportation also need to find out the life cycle analysis of the process. Whatever the other costs also involved, you need to include it. So instead of proposing system at one place, you can propose a system at multiple places. And so that suppose you want to install the system at Banjul, where a lot of agricultural lands are there, right? So there you can able to produce the ammonia fertilizer, you can sell it. So instead of producing from the, I can say, Thuthukudi, you are going to transport it here. I know everything is added into the cost of the fertilizer. Okay. So instead of producing at one point, you can produce at distributed point. So reduce greenhouse emissions, potential for on-site production, everywhere you can produce it. Flexibility, you can install a system, I can say, not like hammer boards, you need several years to commission the system. Here you can able to install a system within a minimum time. Product purity, so without need for any purification process, because the purification stuff in hammer boards, so they are spending a lot of money in getting high purity ammonia. Here, our system is the ammonia is produced from the hydrogen, I can say, from the hydrogen from the water. So the purity is not going to be a question because the separation of other gases than the ammonia, right? In hammer boards, we are going to spend more money. Carbon can be captured, NOx can, I can say the NOx formations are going to be like a NOx. Products are going to be NO, NO2, NO3, all the products are also going to separate out then to take out the ammonia. So the amount of energy as well as the cost involved for purification is going to be very high in hammer board. That's not a problem for our economy. Challenges and research focus. So what are the research scope for this method? Challenges is we cannot produce what hammer boards method produce the ammonia. Current methods are struggle to produce ammonia at commercial viable rates. Suppose we are producing ammonia from hammer boards maybe around I can say $2 per kg or something. Here it will be slightly higher, maybe $10 or 20 initially. Right? Then high resistance hinders efficient energy transfer, particularly in solid state electrolytes. Reaction kinetics, nitrogen reduction, because you need more energy for breaking the triple bond which there in the nitrogen. That takes more energy, right? So that the reaction kinetics plays a major role, and the selection of the catalytic materials also plays a major role to break down the activation energy which is needed for breaking down the nitrogen molecules. Breaking oxygen molecule is very easy because the O and O is connected the double bond, whereas the nitrogen is triple bond. So in order to break the nitrogen triple bond into a single bond, we need to provide more energy from the south. Okay. So sir, the scale up. While electrochemical approach holds a promise for green ammonia synthesis, scaling from lab scale to industrial scale is still a challenge. So we are saying that we are producing, having it's a 1 kilowatt system at our end in Tiruchi, right? Maybe I can go for 2 kilowatt or 3 kilowatt. I cannot go for, maybe I cannot say that I'm going to produce 1,000 tons per day. It's not possible. It's not system. Needs to, lot of research needed to bring that scale to what the hammer boards method people are producing ammonia. Development and efficient selective electrocatalyst, nitrogen reduction reactions, and the can say oxidation reactions. You need a right catalyst for enhancing the reaction at both the anode side and cathode side. Novel materials people are still working on selecting the right material at a lower cost. So explore material like transit metal, nitrates, metal organic framework. So going for a single material, you can go for bi-metal catalyst, which has one is going to be low cost, another is going to be high, so that we can able to reduce the catalyst cost, which can be used for reaction. We need to modify the catalyst for the new advancement methodologies. Maybe plasma also one of the method in which you can modify increase the surface area of the catalyst. There are several ways you can vary the surface area. Okay. Maybe you convert it to minimum to can say micron or micron to nano, or from nano to 10 power minus 2 also increase the surface area of the catalyst, that we can able to I can say further reduction in the activation energy for enhancing the reactions. And a lot of research currently going on with the simulation of the catalyst without trying the catalyst for a number of times. People are going for the method of, I can say, the simulation method, the optimizing the catalyst. So opportunities for the researchers, electrolyte optimization, explore different electrolytes, aqueous, molten salt, solid state to improve the performance, cell design, optimize the cell configuration for efficient ion transport and mass transfer, fine-tuned parameters like temperature, pressure, and current density. So these are the areas. No, people are not only, I can say, the materials perspective, but also the design aspect. Also, a lot of people are working on it. How to have the produce the ammonia at a lower size. So the people are working on it. Challenges bringing the solar and wind as this intermittent energy. So how continuously you are going to produce the, I can say, ammonia from the electrochemical method is a real challenge, because we are going to take the energy from the renewable energy sources. You need some kind of storage system to continuously provide energy without any intermittence. So we have to depend on the batteries and the hydrogen storage system, where you can find out the suitable method of storing the energy promptly. So then grid integration. Now you come across the microgrid and the smart grid and all. So when you want to install this kind of system, now I can say you need to separately design the grid system for renewable energy system. So a lot of new grid systems people are doing a lot of research in that area also. Now the people are talking about microgrid to smart grid. So need to think about what the system need to be brought in, so that the energy can be stored and the required voltage or current can be supplied for the reaction. So the life cycle analysis, people may be new to this area, but lot of can say employment is going on in this area, particularly for life cycle assessment of the proposed system you want to implement. Suppose you want to install a new ammonia system which has your configuration systems, and people will evaluate how the system will be better than the Habermas system or the electrolyzer ammonia generation system. So they will go for a life cycle LCA, life cycle and environmental impact analysis, to ensure that your system in terms of economical perspective, in terms of emissions perspective, in terms of operating perspective. So this is the LCA analysis also. A lot of people are working on it in terms of individual system and also for the total system from the input to the output. Opportunities here: reduce carbon. What are the ways in which you can able to reduce the carbon footprint? How to reduce the water consumption, because we are consuming water for producing hydrogen, which can be used for ammonia generation. So how minimum water can be used for producing the ammonia? Land use. So after the process happening, the ammonia production facility should not create any kind of, I can say, issue to the local environment, and also you need to can say acquire land for installing your system. So assess the potential impacts of on biodiversity and ecosystem. So this is ammonia is also something like falls in the greenhouse gas emissions. So creating the ammonia to the environment, sending ammonia to the environment, there is a possibility of depletion of ozone or something like this is there. So need to prove that your system is not going to degrade our environment. So everything can be possible in LCA. So by addressing the challenges and capitalizing on opportunities, researchers and industry can contribute to the advancement of green ammonia synthesis and eventual commercialization. So I said already, rather than using different catalysts or selecting the best catalyst, there are developing more efficient catalysts possibly identified through density functional theory studies, computational study, can boost the ammonia production. Optimized electrolytes, using electrolytes, high content, how much the quantity of the catalyst electrolyte can be utilized for enhancing the performance. Need to optimize it. There are several optimization tools are available to optimize the several parameters. People are now moving towards the artificial intelligence. Then, right, they're making use of a tool for doing several processes without taking into the experimentation. Then process condition, we need to ensure that we're going to get the maximum yield at a minimum temperature and minimum pressure, minimum water consumption, and also the low cost catalyst to produce the ammonia. So I will stop with respect to this now. So I'm going to distribute the Euro sheet to everyone. And yesterday we have discussed one assignment, right? What is that assignment? Yesterday we discussed about assignment. So something is there in your mind now. So there are people talking about green and this thing now. Suppose assume that you are going to start a company. You have some ideas now, right? I don't want any theory to write all those things. I want what you want to be. Suppose you want to eliminate hammer force, or I want to keep the hammer force. I'm not saying that you need to move to this area. What is there in your mind? Sir, I'm going to keep the hammer force and bringing my technology, my ideas into that. I don't want CO2 can be, I can say, coming out or greenwood can be captured some methodology or something. I am going to distribute the A0 sheet now. Suppose you are going to start a company with hammer force, the conventional method. Right? What may be the new changes you are going to bring? Suppose, sir, I not regards so much of flaws, so much of disadvantages are there. Sir, I have something in my mind. So I am from Tanjore, I am from Thoothukudi. Sir, I want to create ammonia. I want to produce the ammonia. Right? What are the system you are going to bring? Right? So I will give you maybe I can say 10 to 15 minutes time. You can imagine. Suppose you are going to have a company which has the green ammonia generation. What are the different components you brought? Don't think that these are the things you discussed. Maybe you can produce ammonia, and produce hydrogen, not only from the water. Maybe you have some technology, you know that. So you want only hydrogen. I have some resource to bring the hydrogen. Then I want to produce the ammonia. Okay, so imagine this way. If you want to keep the hammer, and if you want to utilize the hammer process or hammer system already existing SMR with hammer post, sir, I want to completely eliminate CO2. Still, I am saying that hammer post system with SMR or conventional method is going to be better than green. There is no need of green ammonia. That also you prove that. Or, sir, I don't want the SMR along with hammer post. I want only green ammonia, but something is there in my mind to reflect it. Okay? So you can proceed. You some drawing. Maybe I can say I may call randomly to discuss. Maybe right or wrong, it's not an issue. The right or wrong is not an issue because I was in the beginning of the session. But something from the last day lecture, you create whether it is 99.9% error, no problem. But when the lectures are keep continuing, then you can able to identify which area I need to change. After the tea break, we'll break for it. So yesterday we have given the assignment, the comparative analysis of global green ammonia projects. We have discussed across the globe, Australia, Saudi, Europe, Japan, or United States. So analyze the project goals, focus areas, and renewable resources, and experimental impact. Maybe you need a laptop now to do it. I don't think everyone is having that. Maybe you can keep this one, maybe for tomorrow, come for the tomorrow session. You can try to analyze it. Because when you want to have, I can say, different projects across the globe. So what are things are there in Australia? What are things are there in Saudi Arabia, Europe, and Japan? And what is there in United States? What is there in India? So from there, you will be able to understand that what is their project goals, what is their focus area, what are the renewable resources they are bringing in for the system. So then you can challenge us, we can really think about whether the system is going to be perfect among the different regions. Okay, so that also need, whenever you want to start a company or something, need to know that what is really going on across the particular place. Okay, So our idea is to ensure that different projects across the world happening. And what is the ultimate aim in focusing on all the green projects? So who is going to be successful? Who is successful till now? Who is going to be successful in the near future? Then need to analyze it. So this is the different projects. You already know that what are the components are there. And I want you from your side, as you are come across with many renewable sources or different waste material come across. Is there any possible to bring those things in your imagination or in your interest to convert that one into hydrogen, which can be used for ammonia generation, or you can bring. There are two concepts. One is we need hydrogen, another is we need nitrogen. So nitrogen normally we are using PSA technology. Suppose you have anything in your mind. There are, sir, I come from the industry background where this method, PSA method, better than the PSA method, some methods we can have to also think about that. Okay, because nitrogen generation also cost is involved in terms of membrane and in terms of the pressure you to maintain at the inlet and exit of the membrane. So some thinking also I am expecting from you. And I said, right, in our laboratory, we are producing hydrogen, not only from the electrolysis process, but also producing from the gasification. Right, suppose, sir, I have so much of waste biomass materials are nearby my place. So I want to use that material for producing the hydrogen. So I have something in my mind to produce hydrogen. And by doing so, I am going to save the environment by clearing the waste generated across the place, and also there is a potential of getting the revenue out of this my idea that also we can take. So hydrogen generation, one of the thing is people are using the electrolysis, but that is not the only method. You can also think about producing hydrogen and lower cost by consuming the lower energy. Is there any possibilities there? You can also think of. Maybe biological method of producing also there, because others we are not belongs to biological, maybe who may be discussing that. We are working on electrochemical and thermochemical conversion systems. Okay. So other than that, maybe you have any other thing in your mind to produce hydrogen, because hydrogen generation is going to play a major role for producing the ammonia. So if any industry is working on that to produce the hydrogen for maybe for kg or something, or maybe a few milligrams of hydrogen or grams of hydrogen at a lower cost than the conventional some or hyperbolic method or the electrolysis, then we can really think about bringing that in realistic way. Sending the program, well and good, you are going to gain some knowledge, but take away from the program is very, very important. So these are all the websites we have used for preparing that PPT. You can also use that, you can explore it, what is going on in India, what is going on in Trichy. So you are surprised to see that in the Trichy Corporation doing a lot of initiatives to segregate the most precious materials present in the, I can say, the waste comes out from each house or from the industry or from the different shopping malls. So they are doing lot of people are working on it, lot of revenues are generating by these different agencies are. So employment also given to the people also. And after that, they are going to dump the unused one. Maybe there is no value, thinking that there is no value in that product. They are dumping into the place called here to the people, the cartoon or they are dumping it. So that is that you can able to get the raw material and the free of cost also. Maybe for transportation alone, you are going to spend it. So explore what is the possibility of using that raw material. By doing so, you are saving the environment. You are also getting revenue out of that. So you can see that in Sengipati near to that, there's a plant called one plant is there to take care of the medical waste generated across the Tiruchirappalli. So they are making use of that waste into a profitable industry. So think about doing something which already people are doing. Think about something which is people are not able to touch, that we have the possibility to do the revenue out of it. A lot of young engineers graduate from IITs or from other institutions, we came to know that from one of the meeting, they started their own company in Bangalore or maybe in Chennai. They are doing a lot of good things. Clearing their waste, they are getting a lot of revenue. So turnover is also going to be appreciable one. So some kind of initiative that people are now need of, I can say, vehicle or the combustion or electricity from the renewable. How the biomass substances or the waste comes out is going to be create a problem to the environment. Just any scope in doing research in producing the hydrogen or ammonia, then you have a lot of, I can say, people are ready to invest also now. A lot of industry, even energy, we have a steady Section 8 company. You bring your idea, they are ready to give money. Money is not an issue. Only thing you come to justifying your research or the invention, which can be appreciable by the industry. You cannot do, we are doing research for academic to get the PhD degree or something. But when industries are coming with some idea, right, you are going to, I can say, competitive with other industries working in the relevant area. You need to prove that you are better than those industries. So competitive. So our thing is not you want to publish a paper or patent, that's all. Nobody will question us. Let's take it to the next level. But the industry, they want to successful in their career. They need to really do a lot of homework and they need to really be inventive. There are a lot of funds are given. Many, I can say, IITs or NITs or industries are running a lot of initiatives, ministry also, now DST also, providing a lot of fund for the youngsters to start a startup. Funding is not an issue. So people saying that I don't have fund and all. But you go with the idea, go to the company, say that I'm going to so protect your idea first. It's very important. In order to talk with the industry, you should be very careful. You protect your idea in terms of IPR or something, then you take your ideas. Maybe I can say, unless somebody will know, take your idea. You must have very carefully talking to the industry. Thank you so much. We'll break for tea. Maybe after the break, we will